A 10-kilogram cart rests on a 37-degree incline, and a 15-kilogram cart rests on a 53-degree incline. A cord connects the carts over a small, frictionless pulley, and the carts roll with negligible friction. We need the common acceleration of the carts and the tension in the cord. This is a coupled system problem. Each cart needs its own force diagram and Newton's second law equation, while the cord links their motions. Use the full Newton's second law strategy. First, draw a free body diagram. Second, define coordinate axes. Third, decompose forces into components. Fourth, write Newton's second law equations. We apply all four steps to each cart separately. The cord then provides the connection. When one cart moves a certain distance, the other moves the same distance, so their acceleration magnitudes are equal. For cart 1, include its weight, m1g, the normal force, n1, and the cord tension, T1. There is no friction force because the cart rolls freely with negligible resistance. Cart 2 has the same three types of external force: its weight, m2g, the normal force, n2, and the tension, T2. Draw the tensions separately at first. Their equality will require information about the pulley, not Newton's third law between the carts. The 15-kilogram cart is both heavier and on the steeper incline, so assume cart 2 accelerates down its incline and cart 1 accelerates up its incline. For each cart, choose positive x along that assumed motion and positive y perpendicular to the surface. The direction choice is an assumption, not a guess, that can ruin the solution. If the calculated acceleration is negative, the carts simply move opposite to the arrows we selected. Only gravity needs to be decomposed. For cart 1, draw the right triangle with m1g as its hypotenuse. The angle between gravity and the inward normal direction equals the incline angle, theta 1. The component parallel to the incline is opposite that angle, so its magnitude is mg sine theta. The perpendicular component is adjacent to the angle, so its magnitude is mg cosine theta. The triangle, not a memorized rule, tells us which function to use. For cart 1, the parallel gravity component points opposite positive x1. For cart 2, it points along positive x2. Both perpendicular components point into their surfaces, opposite positive y. Now, write Newton's second law in both directions for each cart. For cart 1, tension minus m1g sine theta 1 equals m1a. Perpendicular to the incline, n1 minus m1g cosine theta 1 equals 0. For cart 2, m2g sine theta 2 minus tension equals m2a. Its perpendicular equation is n2 minus m2g cosine theta 2 equals 0. We have 4 equations, but 5 unknowns: acceleration, 2 tensions, and 2 normal forces. The taut, inextensible cord makes the acceleration magnitudes equal. The small frictionless pulley also lets us set T1 equal to T2, so both tensions become one unknown, T. Equal tension is not a third law conclusion, and is not automatic for every pulley. If the pulley had significant rotational inertia, or resistance, the two tensions could differ. Here, the problem wording supplies the condition we need. The perpendicular equations would give the two normal forces, but the problem does not ask for them, and no friction relation needs them. Use the two along-slope equations. Solve the cart 1 equation for t. Then, substitute that expression into the cart 2 equation. Collecting the acceleration terms gives m1 plus m2 times a equal to the cart 2 downhill gravity component minus the cart 1 downhill gravity component. The two parallel gravity components compete, so their difference drives the system. Substitute the given masses and angles. The acceleration is 2.34 meters per second squared. It is positive, so our assumed direction is correct. The 15-kilogram cart moves down its incline, while the 10-kilogram cart moves up. Use either a long slope equation for the tension. From cart 1, T equals m1a plus m1g sine of theta 1. This gives 82.3 newtons. As a check, the cart 2 equation gives the same tension. M2G sine theta 2 minus M2A equals 82.3 newtons. The carts accelerate at 2.34 meters per second squared, with the 15 kilogram cart moving down its incline. The cord tension is 82.3 newtons. The reusable method is the full 4-step Newton's second law strategy. Draw a free body diagram, define coordinate axes, decompose forces into components, and write Newton's second law equations. After those 4 steps, apply the physical constraints supplied by the cord and pulley. Keeping those constraints separate makes the method reusable when a later problem changes the pulley or the connection.